Good morning, everyone, and welcome to the 53rd monthly talk of the Rail Enthusiast Society. We had started these talks during COVID because we could not have any other outdoor activity. But I find that the talks are now very well established, and we are now in our 53rd talk. I would like to introduce Mr. Salim Basha, who is the speaker for today. In spite of being the newest member of the Rail Enthusiast Society, he has nevertheless volunteered to deliver this month's talk, for which he is definitely most qualified and suitable. With more than 17 years experience in the railway industry, Salim Basha is currently the regional product manager and the recognized Bogies Expert at Alstom Transport. He is responsible for the right product identification for current and future markets, portfolio management, and is an expert competency development of the site. His past roles include engineering development activities such as leading the system and detailed design, FE analysis, design reviews, drawing creation, supply analyzing, build and validation tests. So he is definitely very qualified to deliver today's talk. So over to Mr. Basha.
Okay, thank you. Thank you for the introduction, sir. So good morning, everyone. I'll share my screen and try to run through the talk that I want to give. Okay, sir. So good morning and thank you, JL, sir, for the quick introduction. So my name is Salim Basha. I am the regional product manager working in Alstom. And today we'll try to look at the bogies. I'm the bogie engineer or recognized expert in Alstom. So I will be talking more about how do we design a bogie and how do we commission it. So that will be the topic of today's discussion. There are about 12 slides and I'll try to keep it spend around 3 to 4 minutes on each slide. So in 45 minutes, hopefully we should be able to finish and then we'll take the questions as necessary. So we get started. Okay. So before I go ahead, I just want to give a little bit more about my background. As you can see here, I'm the regional product manager for the bogies working in Alstom. And for those all of us are aware, but this is what we mean by bogies, which are the underside of a locomotive or a carriage that we see. So this is what I design and develop in my company that I'm working. Let me go to a laser pointer. So I did my BE in automobile engineering in 2002, did my master's in machine design in 2005 from Bangalore University. There was a short stint in Honeywell, and then I moved on to railway domain because I come from a railway background, and I wanted to be in this domain. And luckily, in the beginning of my career itself, I got an opportunity to get started with GE Transportation, which is now a Wabtec company. That is where you can see I have spent about 13 years of my life. I started as a FEA, finite element analysis engineer, and a structural engineer, trying to work on a computer, doing some analysis, and that sort of my initial role was doing some stress and strain analysis. Once I was successful in that, I spent about 3 to 5 years there, and then I was moved to a component engineer, owning the frame. So I got to know how to design a frame, be it a fabricated frame or a casting frame. How do we design it? How do we validate it? Doing the bolted joint calculations, welded joints, casting designs, so on and so forth. And then I also became a brakes engineer, doing the brake calculations, stopping distance, decelerations, and doing some Excel calculations to do the stopping distance calculations. And once I was good in these two components, I was made a systems engineer. Systems engineer means when you put everything together as a bogie, how does it work? So that is something that I had owned in G. So doing the multi-body dynamics, the spring mass damping, how does it work when you put up together? Doing the tolerance stack-ups of the bogies and controlling the weight and height of the bogies, and liaising with the other cardboard engineers to ensure that the entire locomotive that we make is really meeting the performance. The bogie is meeting the performance which is expected out of the locomotive. And then I was also involved in testing and commissioning. I traveled across the globe to some good countries, even to TTCI in USA, wherein we have tested one locomotive on the dedicated test tracks. So I was part of the team which went there, putting some strain gauges, accelerometers, and doing some correlations with the simulation that we have done earlier in the program. So that is my life in GE Transportation until 2020. Then I moved to Alstom Transport, which is a much more wider organization in terms of rolling stock. We make too many rolling stock, be it a tram, all the way to high-speed trains and to a locomotive. So it's a wide range of bogies that we make, wide range of rolling stock that we make, and it gave me an opportunity to widen my horizon of my bogie knowledge. I started as a program manager, like I was doing systems engineering, and it's more like a managerial role, as you can see, managing the cost schedules and system engineering. And then very recently, a couple of years ago, I became the product manager. By product manager, we mean it's more about the product. How do we make the product robust and for all the markets, without keep on developing a new bogie for every every project that we have on hand. So that is my current role, which is ongoing. And you can also see that I have given some lectures in GSV Baroda and earlier this year in March 2025. And I have also gone on a rail fanning trip. You can see Hapurva here and other stalwarts. I'm also part of doing little bit of rail fanning whenever my time allows. So that's about me, a quick introduction. And then we jump on to the topic. So what we talk about is the bogies design. Where do we start? What do we do? What simulations we do? How do we validate that? And how do we commission it? And how do we end the process? So how does it actually starts? So this is more like a project-based agenda that you will see, wherein it starts with a technical specification. So I take an example of a locomotive, like in 2020, 2015, we had the GE Transportation had given a locomotive for Indian Railways, and the specifications was written by RDSO, and this is the starting point of us. So this is the specification for the entire locomotive. This is what Indian Railways needs at that point of time. So that they write a clear spec of what is that is expected out of a locomotive. Now, as a bogie engineer, there are few things that I will focus on, which has been written in the second column here. So what is the haulage capacity? The haulage capacity of the locomotive, RDSO needs it to be around 540 kilonewton. By haulage capacity, what I mean is the force that we can generate at the coupler so that it can pull the right amount of, it can pull the train. And then they also say that I cannot exceed my axle load beyond 22 tons. And then my speed is going to be 100 kilometer per hour. Good. And then they also specify the track condition. So this is how the track would be. The characteristics of the track would be defined in a certain document, which is called C&M Volume 1. So I need to ensure that my locomotive should be able to run at 100 kilometer per hour on the track conditions defined by C&M Volume 1 document. And they also define the gauge that my locomotive cannot be wider than this or it cannot be taller than this, because this is my scope. This is my gauge that I need to follow. So it is also defined like a MMD diagram. And then the bogies type is also defined pretty much. I need a Coco bogie or a Bobo. So here it is Coco for sure. And then I also check for what is the stopping distance requirement. And here, for example, they have specified about 600 meters when running at 100 kilometer per hour. So it has to come in 600 meters uh, to stop within 600 meters. So these are the key data points that I would look for while designing a bogie. And there are more of it, like the temperatures. Temperature also plays a big role, because if you take a rubber element, for example, a rubber bushing, it behaves differently in plus 30 degrees Celsius, and it totally differently in minus 20 degrees Celsius. So we need to ensure that in this temperature range, whatever stiffness we consider for the rubber bushing is still within the range, and it meets the requirement. So that sort of temperature plays a big role in the design activities that we do. And we also specify the noise that we can tolerate. We should not be able to exceed those limits. And the key thing is maintenance schedule. So we need to ensure that the bogies that we make should be maintainable, or it should not need frequent intervention or frequent maintenance. So that those are the key things that will get defined. So this is the starting point of a bogie design. So which clearly defines what is needed out of a bogie. And now, before going too much into the bogie, I just want to get started with how do we basically lay out the train. So what happens is that, okay, now that we know what is our customer wanting, and then we try to first make a concept out of what is needed. Like, okay, they need a locomotive. Okay, fine. What engine we have this engine, we have to put this engine there. So basically we try to locate all the apparatus into the locomotive and try to make a very preliminary layout of the locomotive, and we define where the bogie should be located, what space we have to put our equipment, what space we have to put the engine, to put the electronics, and then the radiators and the driver cabin. So we put across those layout. We always focus on the packaging, that the layout is well packaged and well balanced. We don't want the front bogie to weigh more than the rear bogie. So that sort of criteria are kept in mind, and we lay out the equipment in a way that we are able to meet the axle load and be able to fit the gauge. So when I say the gauge, so we have different gauges. I just took an example here. You can see the various constraints we have in terms of gauge. Great Britain is very tight. They call for a very short and a very almost a good narrow locomotive. But as you move towards right, Europe is little better. Belgium, Central Europe, and USSR. So each country has their own way of defining the gauge limits, and we need to respect that. So keeping this as our inputs, we try to make a quick layout of the locomotive. Now, when it comes to where to space the bogies, here in this locomotive, for example, you have spaced it at around 9700 mm. So what are the parameters which will tell how much we need to space it apart? So two things mainly come into picture. One is the strength of the underframe. Of course, you can see the right side picture here. Not going into much of detail. This is the analysis that we do of the loading that is going to come on this structure, and then keeping at certain distance, what is the loads that this structure would see, and is it still within the limits or not. So we try to place the bogies which are completely balancing this load. And then also the fact that when the train goes on a curve, it has some corners which will go out of the gauge. So we do those calculations as well to find out how much of span we need to keep for the bogies and how much of overhang we can actually provide. And remember that we need to also package this equipment within this given length of the locomotive that we have. So then we do these calculations, the overthrow calculations. You can see the end throw and the center throws that has to be calculated when the train goes on a curve, and we need to cut out these protrusions so that it does not infringe the gauge diagram. So at a train level, these are the key inputs that goes into to define the layout of a train, or a layout of a locomotive, where to keep the bogies, how much far we can space them apart, and what is the total length of the locomotive that we can go about, which will meet all these criteria which comes from the customer, and then we have our own design constraints. So this is how the train layout will get defined. And then I go to the bogies design. Like so once the train has been decided, we make the computer models of the train, and then we try to simulate them the train as a whole, to see whether it is meeting the requirements or not. So we all know the wheel set principle, how the wheels are tapered, like this bicone that you see here, which is needed for it to stabilize. I mean, to allow it to take a curve without getting slipped. So that sort of a mechanism is playing a role here. So we have this wheel set. Now this wheel set has certain requirements. Like when it goes on a curve, we need to ensure that it does not derail. So what happens is that we have this flange which is meant to stop it from derailing when it is going on a curve. And then we need to, and what makes the wheel derail is the forces which are trying to lift the wheel up. Like when you go on a curve, your lateral forces are higher, and that force tries to pull this wheel set up, and the wheel set force, which is the force which is trying to put it back on the rail, is the vertical force. So so here we try to do some simulations and find out how these forces behave over the time, and are we still within the safe zones. So there are some basic equations, will not go in detail, but which define what are the limits of my lateral force that I should not be able, that I should not cross, or L by V's that I should not cross. So this is the situation on the curve, that we have this bicone wheel which is helping us to take the curve easily. But the same wheel set, when it goes, when we place it on the straight track, by design, by virtue of its twin tapered design, it is going to oscillate something like this, which is also called as hunting. So we need to ensure that this hunting is minimized or controlled, so that it does not oscillate and it does not create a very resonant condition and the train jumps off the track. So these are the two contrasting requirements that we have when we design the train, that it should be able to negotiate a curve without the forces going beyond the limits which will derail the train, and on the same time it should not be so stiff. I mean, it should be enough stiff that it should not keep on oscillating and then creating a hunting situation when it's going on a straight track. So keeping this in mind, we make the multi-body dynamics model. Like each and every body is defined as a concentrated mass, and we model the spring damping, the stiffness and the damping into the system. You can see that how it is generally created. And I'm going to play this video, which exactly tells how the simulations are done. Uh, One second. For some reason, I'm not able to. Okay, before I play the video, I want to explain what this video is. You can see it's a computer model. It is pretty much representation of the picture that you see on the top. So you have a car body, you have two bogies. The bogie has been modeled like this V-shaped item that you see here, and then you have modeled all the springs and the dampers that constitute this locomotive, and then we also model the track. So we model the track and we also model the curvatures, some representative curvature or the tightest curve that it has to take. And then we try to run this simulation and we try to monitor these two arrows that you see. We do it in numbers, but just for visualization, you can see that trying to show how these vertical forces are behaving over the time and how does the lateral forces get generated. So I'll quickly play this video, which tells how these forces get generated when the train moves. So it's going on a curve. We can see that the lateral forces are getting generated. So we can easily, we get to know what those forces are. And then we compare with the limits. And then it has come back to a straight track. You can see the lateral forces are reduced. Now it takes the turn in the opposite direction. Yes. So you can see that this is what the other sided lateral forces are getting generated. So this is how we model, simulate, and iterate on a computer to ensure that all the safety critical parameters are maintained. So this is what we do in terms of the first level of train system simulations. Okay, so once we exactly know the train level definition is defined, this is going to be my length of the locomotive, this is where I'm going to place my bogies. um, so then the next level of system, which is a bogie system, is defined. Like what spacing should I place for the wheel set, what should be my wheelbase, and what should be my suspension stiffness. So at a system level we try to define the bogie. So at higher level, in the previous slide we defined how the architecture should be, and now here we are converting that architecture into a CAD, uh, a, into a 3D model, that okay, this is what is expected from that architecture. So this is how we will try to package that bogie, and this is how we are going to install our coil springs and dampers, and then sizing it accordingly, so that this bogie is built. So here you can see that when you break it down, it has all. This is the primary suspension, which is between the wheel set and the bogie frame. You have the coil springs, you have the rubber pads, and you have the spring, the lower spring guide, which is this is nothing but this is the guide element which will try to guide the wheel set accordingly on when it goes on a straight track or on the curve. So we do that, and this is the anti-roll bar that you see here. This is the primary suspension, and between the car body and the bogie frame, we have another set of suspension, which is called the secondary suspension, which has maybe a coil spring, or it could also have a rubber pad, or it could have an air spring as well. And then sometimes this is an LHB bogie. That's why you see a bolster between the car body and the bogie frame. But even otherwise, we can directly mount it to the car body as well. So here is where the system level, a system layout of the bogie is been imagined or is been developed. So the key parameters which are taken into our consideration is like whatever has been simulated in the earlier slide have been accommodated here. Like the like for example, the simulations will say that I want a damping of certain amount, and I need to ensure that I get the damper of that damping capability, and I'm able to mount it at the right location, and I'm able to package it without it hitting the frame or coming out of the gauge. So those type of detailed analysis is done at this stage, and try to package it with some realistic constraints that we have. So stability, ride quality, and interfaces, and then the relative motions and clearances. So the bogie and the car body are not static; they keep on moving. There will be a relative motion between those. So we need to ensure that until the hard stops are hit, no other component hits the other part of the car body. And then we also need to ensure that the mass of the bogie, the height of the bogie, because it's all defined by the platform heights, the height has to be within some limit. So that also comes from the train engineer, that my bogie cannot be taller than certain height. So we need to package it within that. And also the mass, the whole locomotive is supposed to be of certain mass, and they will allocate some masses for the bogies. I need to ensure that my bogie does not cross that allocation. So that level of analysis is done at system level. I'm trying to show that in this slide. So I take two components, for example. So now that we know how the bogie is going to look like, the next stage is taking a component here, frame, for example, and trying to analyze it and ensure that it meets the requirements. So how we design the frame is like, see, many times we see it's like it could be like a catch 22 situation. Like we don't know what loads we need to apply on the frame because we haven't run the train on the realistic track, and we don't know what force are really getting generated. So to solve that's of that type of a question, we have these international standards which have done enough research in the past, and they know that typically on a frame these are the loads that are going to come. These are the vertical loads that are going to come. These are lateral loads, and this is the twist loads, and so on and so forth for this typical type of tracks that we have. So these standards pretty much define what forces we need to consider to design the frame. And we model the frame in a CAD model like as we want, given the constraints that we have. And then we have some softwares like the finite element analysis softwares, wherein we try to apply those forces and then try to see what are the stresses that are coming up. Are the stresses within the limits or not? And if they are not within the limits, then we keep on iterating the design to ensure that it is meeting the stresses are lower the limit. So we make the CAD model, then we push it into the FEA regime, and we do the FE analysis, and this is the output of an FE. You can see that different colors are there. So what it says is that anywhere where it is expected to fail, we'll be throwing it up like a red color. So this is my region where it might probably fail, or this is where the stresses are going beyond the limit. So this is where I need to redesign the frame and ensure that it does not cross the stress limits. So we do that. And then we also need to compare against the various, like for example, here, this is a fabricated frame. And how do we know what is the limit of that joint? Because each weld behaves differently. So the welding itself is a different technology. So people have created different type of welds, and they have tested the endurance of that weld. So different welds, for example, here you can see that the weld is along the stress, like wherever the load is along the weld is along the loading direction. So it will be a much stronger design. But if the weld is against the load is trying to tear apart the weld, it is going to have a lower strength than the weld which is along the load. So we try to get this data. There are again international standards which are written about a welded design. So they define the strength of different type of welded joints, and we compare against the stresses that we get here. So this is how we come to a conclusion that yes, we iterate the design and ensure that the welds are taken care of and they don't fail. And then once we are all sure that we have done a good job in designing the frame, we go and create the drawings. You can see that this is how we create the drawings. The parts are cut, the metal is cut, the and into different plates, and we put them together, weld them together, and we make the frame. So after making the frame, we even have to run it through the bench test. If it is a new frame, the standards call us to test the frame on a static bench to ensure that it does not fail. I mean, they define a certain range of loads that this frame has to endure. And if the frame is not failing post that test, we can say that this frame may never fail in the field. So we put it under a bench. You can see that this bogie has been placed here. Some hydraulic jacks are placed here. They apply the load, all the dynamic loads which will come onto this frame. And we also measure the stresses. We put some strain gauges at the critical locations as defined by the FEA analysis. So we put it and then uh, try to correlate the stresses. Like, I predicted the stress to be so much. I'm now testing it now. Am I really getting the stress what I predicted? Am I getting it higher? If I'm getting it higher, then something is wrong. I need to do something about it. So we do those correlations, and then any modification that we have to do on the frame. So that would be done. So once we do all those modifications, we retest the frame, and if the frame passes that bench test, we say that the frame has passed the qualification test. Now it is good to put under a locomotive or a train, and then continue making the train. So this is how a frame, for example, is designed. A bogie frame is designed, manufactured, tested, and commissioned. Okay. So I take one more example or two more examples here. The wheel set, for example. The wheel set as well gets designed based on the different loads that come onto it. I'm just showing some textbook examples here. You might have seen um, like in your in our maybe high school or pre-engineering, we see that this is how the loading of a typical axle is. You have the load which comes and then it bends the axle. So this is how the bending diagrams are created. So we develop this bending diagrams, and then we try to find out whether they are going beyond the limits or not. And then we try to size the axle, like what should be the minimum diameter of the axle should be, so that it does not cross its the stressor don't cross its limit, or it is strong enough to take the loads which are coming onto it. And then there are different aspects. This is the axle will get loaded because of the vertical load. So in a static vertical load, it's going to be something like this. And if you on top of it, if you have a lateral load coming onto it, you have additional lateral component, additional bending component which will get added, and then it is going to load the axle further. So we need to take care of that. And then we have this the tractive effort and the braking loads as well, which will get applied in a different plane, and they generate a different set of loadings. So we need to combine all these and then ensure that the axle has been sized for to take up all these loads. So this is about the wheel set. And then talking about the brakes, the next component that we design is the brakes. And to start with, designing the brake it's like high school physics, like as I have mentioned here. Like, we have seen these equations in our high school, and the same equations with some minor modifications or with some realistic coefficients become the equations for us in real life. But otherwise, the fundamentals is still the same as we might have studied in our high school. Like, v square minus u square is equal to 2as, which is nothing but final velocity to initial velocity is 2 times acceleration into the distance that it covers. So here we are trying to calculate the distance that it can cover. Given the stopping distance, we need to find out what should be the deceleration that I need to apply onto the train so that I'm able to stop it within the specified stopping distance. So I calculate, say, the deceleration A from here. So we know F is equal to ma, so we know the mass of the train. So I will calculate what should be the force that I need to apply, the decelerating force that I need to apply to decelerate that mass. So I calculate my force, and then that's my decelerating force, and then the normal force, the clamping force that I need to put on my brake is calculated based on the friction coefficient. We know that the friction force is like if you take the normal force and divide, yeah, the frictional force is nothing but normal force multiplied by the friction coefficient. So we just take it to the other side and we calculate what should be my normal force that I need to apply to be able to decelerate the train. And then it's all simple high school physics calculations which will tell us what force I need to apply to stop the train in the intended stopping distance that I have. And this is a quite simple analysis, because here everything is unitized. Like you have a thread brake unit, you just put it here. But there are some traditional brakes as well in some of the rolling stock, in some old locomotives or even the freight wagons. So here it's little complicated. Here you have a brake cylinder and then which operates a set of levers. So this leverage is needed to increase the force. In olden days, maybe the brake cylinders were not very capable enough to generate the right stopping force that we need. So we had this leverage mechanism which will amplify the force, and ultimately by the time it comes to the shoe, it is going to be like 10 times or 20 times the force which got generated at the cylinder. So even this is possible. We do this as well, where the cylinder is not capable of generating the force which is needed. So here as well we do some calculations. What is my leverage ratio? How do I size the levers so that I get the same leverage ratios that I want? I want, say, 10 times more force, then I need to size the levers so that I get that leverage over there, given the space constraints that I have. So this is how we kind of design the brakes. Philosophically, I'm talking at a very high level. And now I just talked about the different. I took some two or three components as an example, and I explained how exactly we design that. So once the design is done, everything looks good. We assemble the train, the bogie, and we put it on the train. And now we start the commissioning test. So in the commissioning test, there are two set of tests. One is the static test, and one is the on-track test or the dynamic test. So before going into the dynamic test, once we make the train, we run the static test. So what do we check in static test before taking it onto the track? First and foremost thing is the weight balance. Like whatever I envisioned for the axle load, like what is the limits that we have of the axle loads, am I reaching that or not? And is it perfectly balanced? I want all my axles to be equally loaded, with very minimal variations between the axles, maybe 2%, 4%, whatever it is. So I put my load cells. You can see some load cells under the wheels, and we're trying to first ensure that this train is perfectly balanced. So this is the first test that we do, and if it is not balanced, we need to do some modifications, maybe some layout change or something inside, to ensure that the weight is balanced. Or maybe sometimes it could be a part to part variation, so you can just do some shimming. You put some shims under the springs to increase the load at that particular axle. So we do this weight balancing. And then the next static test is the sway test. Sway is nothing but the ability of the train to sway on either side when it's going on a curve, when it is a super elevated track. So we need to ensure that when it is going on the track, if it is say it has stopped on the track, which is super elevated, it should not roll down or fall on its side. So this is the test that we do to find out whether it's going to be stable when it is lifted on one side, which is the super elevation limit of the track. So we do this, or even it is also applicable for the can deficiencies. We know, like on a curve, the train runs faster than the balance speed, so that the train will tilt on the outside. So we need to also ensure that when it is going at a high speed on a curve, it should not fall on the other side as well. So even for that reason, we do this sway test and ensure that everything is good. Um, the next is the bogie rotational test. If we can look at in detail, we are just trying to rotate the bogie. We keep the car body static. We take the bogie and we rotate it in plane, in the horizontal plane. and it tells us the capability of the bogie to adapt to the curvature. Like you're going on a straight track, you hit a curve, your bogie should be flexible enough to negotiate the curve or follow the curve. If it is too stiff, it can always jump off the track. So this is one test which is called the X factor test or bogie rotational test, wherein we keep the locomotive, rotate the bogie and see whether it is compliant enough or soft enough to take the curvature. There are some limits. It should not be too soft. If it is too soft, then it is going to hunt when it's going on a straight track at a very high speed. So, so this is one test that we do. Now, another test that we do is the wedge test. There are four pictures here. Each is different. So wedge test is nothing but we are trying to find out what is the oscillation phenomenon of that locomotive. Is it like what sort of mode shapes and in what frequency it is going to oscillate, and in what modes in what shapes it's going to oscillate. And the point is that we should have enough damping that if we disturb the locomotive, it should damp down. It should show this type of a scenario wherein it's going on a it's going on a track at a good speed, and then there is some disturbance on the track. So that disturbance should not make it oscillate. It should not oscillate. It should damp down after certain cycles, like this picture what it shows. We don't want this type of a scenario. So here we try to induce that modes. So what we do is we take the entire train. Sorry, is there any question?
Good.
Yeah, sorry. So so we take the entire train above the wedges. So we can see that all the wheels are above the wedges. And then we push the train so that all the wheels come off the wedge simultaneously. So here we are trying to simulate the pure vertical motion and see that how many cycles it takes to damp down. It should take say 3 or 4 cycles. If it is not able to damp down within like 3 or 4 cycles, then my damping is insufficient. So I need to change my damping. And I also check at the frequencies at which it is vibrating, and I need to ensure that it is not close to the other resonant frequencies that might make it oscillate. So these are the things that we check. So we simulate the bouncing mode here. Here you can see that only one bogie is on the wedge. So the moment you push it out of the wedges, it is going to pitch. It's going to make this motion. So we again we find out whether it is damping or not. Similarly, the sway motion, like the roll motion, I would say, we keep the wedges on one side of the wheels. We push it out, and then we see whether the bogie, the train is just settling down straight, or if it keeps on oscillating. And then this is purely a lateral. You push it one side laterally and then release it quickly so that the locomotive will oscillate in plane in this direction, and it should stop oscillating after some time. So these are the static tests that we do at a train level, which will tell us that is this train is stable or not before we take it to the track testing. So so this is about the static test, and then we go
This
to the
test is done
dynamic.
at what speed? On
Uh,
what speed this is done?
This is all static. It's the top three rows are almost zero speed. The bottom one is maybe 3-5 kilometer per hour. I'm not very sure about the number, but it's going to be in single digit.
Okay, thank you.
The wedge test will be in single digit.
Thank you.
Okay. So here is the last slide. Here, once we are sure that the static tests are all coming good, the train is stable, we take it to the track and we do some high speed test or the oscillation trials. And how do we do that? We take the wheel set, for example, and we put all the strain gauges around it. I'll not go in detail, but this is trying to find out what are my wheel rail forces, the forces which are trying to derail the train will be measured by this wheel set. You see the wheel set, you put some strain gauges across it. You can see some small telemetry signal here, some antenna here, so which will measure the strains, and it will try to calculate what is the force which is coming between the wheel and the rail, and then transmit it to the data logger which will be there in the train. So we might instrument one wheel set or all the wheel sets of the train depending on the on the necessity. So this situation will tell us how the vertical and the lateral forces are behaving real time as the train moves, and are we reaching a phase wherein my L by V's is my wheel trying to lift off the rail and trying to derail. So this is how we measure that. Now, we another aspect is like the stability of the train. So we put accelerometers all across the train or at the key locations, which will continuously monitor the vibration characteristics of the train. My car body is expected not to vibrate too much, not to oscillate too much. So we find out a right sweet spot. We put an accelerometer there. Similarly, accelerometers. On the axle box, we put some accelerometers. So, and then we continuously monitor it and try to see if we are able to see any hunting or a unstable condition. So is any of the accelerometer reading out any unstable condition? So we measure that. This is the raw data. We filter it out, and then we do a lot of data churning to find out whether is every signal, every accelerometer gives out on the train. So this is what we do in the stability test. And of course, the last test is the stopping distance test. So we know that from our maybe the first slide that the customer wants the train to stop within certain distance. So these are those tests. So we apply the brake at certain period of time, and then we try to see how much time it took for the speed to reach to zero, and in that duration, how much distance it has traveled, and is it within the limits or not. So different tests that we do. Okay. So yeah, here is where I come to the conclusion. So I hope I try to cover the bogies development. What is our input? What simulations we do? What calculations we do? How each component is designed, validated, and then how do we put them together? How do we test them together statically and then dynamically, and then ensure that the whole train as a system is safe and fit for use. So this is what we do, and it's a structured engineering approach. Like as we said, we conceptualize the ideas, we see what constraints we have, then we put everything on a computer and we try to simulate everything without cutting the metal. We try to simulate, and then we verify. By verify, I mean by all the calculations, everything, even before building the train. And then once we are sure, we build the train, and then we validate it. Looks very simple, straightforward approach, but in reality, this is how it actually goes. We have to iterate. You conceptualize something, you simulate it, you find that something is not good, you want to go back to your concept and try to work on your concept, and then come back to the simulation phase. And it is easy at this phase, and it is cheap as well, that you can always, because everything is on computer, nothing has been cut on the ground. So you do this, then you try to verify it. You may find some issues in your verifications, you come back and maybe tweak your model, and then try to redo things. And it might become little complicated because you might have started already ordering the parts, the long lead parts which are already on ship to reach your place. It becomes little complicated, and it keeps on becoming complicated as you find the mistake late in the design phase or in the development phase. Quite logical, nothing, I don't have to explain in detail, but this is how it goes about. But every time we make a train, we capture the lessons that we have learned in making the train, and we ensure that we don't we capture those lessons, and we ensure that the next train does not have is a improved version of what we have made before. So this is how we run the show here. So yes, I think this is where the slides end. Now I'm open to questions, and I hope I did justice to the expectations which was put forward onto me. And yeah, please let me know.
Thank you very much, Mr. Basha. I think you have managed to uh, condense a very complicated and detailed and long subject into a very short presentation, and in terms that which even I won't say an absolutely non-technical person will understand, but even a semi-technical person will understand. Now,
Yes.
Mr. Anand had put a number of questions in the chat box. So may I request Mr. Anand to please ask his questions? Mr. Anand, please go ahead.
Thank you, Singh. Excellent talk by Salim Basha. I
Thank
mean,
you.
as they say in Hindi, Gagar mein sagar bharna. Whole lot of knowledge in such a small, concentrated package. But when I was in RD, so that was about 40 years ago, things were so different. We did not have any computerized equipment. The biggest computer we had was the IBM 1401 or the IBM 360 at Kanpur IIT. Nevertheless, we did optimize some designs, some which we had taken ready-made. We got some of the ready-made designs were the Schlieren bogie for coaches and the tri-mount, Alco tri-mount bogie for the this
Yes.
thing. So I have only three questions.
Yes.
Uh, in those days, the lock bar used to be a big constraint. The
हेलो
हाँ गुड मॉर्निंग बोले
गुड मॉर्निंग। ये बोल रहे थे आज जो है ईडी साहब को हो सकता है।
Think there is some background here.
Anand sir, go ahead.
Actually, my question is addressed more to the railways than Mr. Salim Basha. There used to be a lock bar for the interlocking system, and the constraint was that no two wheels of any vehicle should be more than 42 feet apart. At any given time, at least one wheel must be on the lock bar. This put a lot of constraints. The other constraint, as far as wagons are concerned, was that there used to be a limitation on the braking forces. The braking force cannot exceed 10% of the gross load of the wagon. I don't know whether that still exists. And then, of course, whether there was any, in your experience, Mr. Basha, whether you found any sweet correlation between the primary spring deflection and the secondary spring deflection.
Okay.
For the Schlieren bogie, it was 50-50. Then some bogies we made with, tried with 30-70, that is, then we made for the meter gauge milk van, we made the bogie with 75% of the deflection in the secondary spring and only 25% to the primary spring.
Mhm.
And of course, those days, very little was known about the actual dynamics. And, starting ab initio from control system theory, but a very seminal paper was published by the Institution of Mechanical Engineers in their journal dated January 1975. It was a theoretical analysis done by Newland and Cassidy. So I think it's very interesting because they tried various inputs, putting in a step input, a ramp input, and an oscillatory input, and then try to analyze with different criteria whether we should adopt Nyquist's criteria or that sort of thing. That's all I have to say. Thank you.
Thank you, sir. Okay.
Mr. A.K. Singh, ED Carriage had a question. Please go ahead, Mr. Singh.
Right, sir. I have a question. You were talking about the unbalanced masses
Yes.
on the say each bogie, each wheel. So, is there any criteria for which you do the fixed value that the variation of the weight should not be more than that much percentage on the each wheel or on the each bogie?
Yeah, I think the EN standards define that pretty much. Like the reason for having same load on each axle is to ensure that it does not, slide and just stick on one side, because the imbalance will try to bias the wheel set, move towards one side. I'm not able to recall the exact numbers, but I think it is 2% on each axle. If you take one axle from left to right, it is 2%, and within the bogie, it should be within 4%. I'm not able to exactly find out a number, but that's what I remember.
Yeah, that's
2%.
what. Yeah, some confusion was there. It's a 2% and 5%, something like that. But exactly that I wanted to know what is the exact percentage. If something is there, you have.
I can check the standards and get back on that, sir, because I'm not
Okay,
able
okay.
to
Yeah, yeah,
remember.
really. Thank you so much.
Yeah.
Mr.
Okay.
Ravi had a couple of questions. Please go ahead.
Yeah, is there any scope for electronics in bogies?
Electronics, yes, huge scope is there, sir, for in electronics in bogie. So basically we want to extend the life of the components, like the bearing, for example. We can always continuously monitor the temperature of the bearing or the vibration of the bearing to estimate the life of the bearing. So yes, it is there, and lot of electronics are already there in the high-speed bogies. The high-speed bogies have something called instability monitoring electronics mounted on it, which will continuously monitor the vibrations. And the moment it is reaching to a limit, it says that stop, please reduce the speed. Maybe this bogie is going to go out of control if you continue to run it in the same way. So we have active monitoring of the signals of the bogies. Electronics is possible.
Yeah, we are marking this question is basically in automobiles, your suspension is dynamically controlled based on the dynamics.
Yes.
So that's the motivation for this question. My second question is how the bogie is different than TGV and bullet trains. Are they different? Are they similar?
Certainly they are different because the application is totally different. So your bullet train and TGV run on a different type of a track. Those tracks have very less curves. They are almost straight track, and the minimum curve maybe 3000 meters. I don't know exactly, and they are generally the slab tracks. So they are meant for the high speed application. So you will make a much stiffer bogie, like which will not yaw too much, a much stiffer bogie in this direction, so that that you're not going to go on a tight curve anyway. So I can be much more stiffer. So basically your suspension changes. So suspension changes based on the track and the speed.
And my last question is what is the future direction on bogies?
What is the future direction on bogies? Okay. I mean, as an organization, we always want much more reliable bogies. The bogie which is which can meet all the requirements and also be maintenance friendly. We extend the life of the components. The biggest item that we bleed the most is the wheel. If you are somehow able to increase the life of the wheel, it'll be a good thing. That is something that we can focus on in future, in near future, I would say.
Okay, that's it. Thanks a lot.
Thank you, sir.
So may I
Mr.
ask?
Tanmay Mehta,
Yeah,
please.
let the
You have some questions. Mr. Tanmay, please go ahead.
So can you hear me right now?
Yes.
Yeah. So Salim, hi. I had worked on the IR20 bogie, which was one of the first Y-frame bogies. So we've done some interesting things out there. Just wanted to bounce some points off you. So there are 4 points. Number one is that when brakes apply, there is a load transfer which short circuits the primary suspension. So on a bogie, one of the axle gets offloaded and the second axle gets heavily onloaded. So that actually causes a change in the way the forces are to be simulated. In the simulation diagram that you had shown, I could not see that being involved. So that first question is, how do you handle the issue of brake applications effect on the primary suspension? So that's question number one. Question number two is, at least as far as I know for Indian Railway broad gauge characteristics, the location of the centroid turns out to be extraordinarily sensitive, especially when we are comparing the UCR and the LCR modes. Indian Railways is very, very sensitive to the LCR mode, and there's a predilection for LCR dropping very low. So again, I'm not very clear how was that issue being handled in your modeling. The third point is there was a very interesting exercise which was done, which involved RDSO way back in the 80s. I haven't seen it duplicated thereafter, where somebody actually measured the PSD of the Indian Railways track versus the speed. And normally, as speed increases, the energy transfer into the bogie keeps on increasing. But that's not true for the Indian Railways. There was a Brel study. I remember seeing the file in RDS1. In fact, I photocopied a couple of pages for them, which I had used as a part of my analysis. But on the Indian Railways, beyond a certain speed, the energy transfer into the bogie from the ground actually reduces. It's an inverted graph. It's a question mark shaped graph. It's not the traditional graph that keeps climbing. Do you factor that in? Is that data still available? Maybe AK Singh can actually add on to that particular piece of information. And the last
Sir,
question.
not readily available. We'll have to check it.
Check kar lena, because I have a couple of pages which I had photocopied out of that report. Use that as a part of the IR20 design, and the results were pretty crazy. Okay, so I'll just take the last part. In the analysis that you have talked about, I didn't see a time domain analysis. So I'm just curious if that's also a part of the bogie design activity that you do, because we did discover that time domain analysis, specifically because of the kind of couplers that we use, has a major impact on ride quality. So just 4 questions. Thanks a lot, yeah.
Okay. I'm just trying to think, how do I reply to those 4 questions? Like, I just lost track of it.
If you want, I can repeat them.
Yeah. The best way what we can do is maybe we can exchange some emails, sir. If you can maybe write it down, I'll also get some time to think about it and try to refer some documents if at all I have to, so that I can positively respond to your queries. So yeah. So I still remember the question. One question was about the brake, about the unloading.
So the
and how
first
do you
question,
manage that?
the first question was a brake, the loading and unloading, which happens on the 2 axles. So one will unload, the other will offload. So
Correct.
onload, sorry. So as a part of the dynamic simulation, when I had done it, I had found that there was a tendency for the primary spring to home, and I actually had to change the design of the primary spring because there was a very high probability of breakage. And this is the IR20 study that we had done. And across the 25 years that IR20 ran, it didn't have primary spring failures, though, and primary spring failures is a major issue happening right now. That's why I asked the question.
Okay. So definitely when there is a braking, there will be a load transfer that happens. Like the front wheel will unload, the rear wheel will offload. At least what I know is that we have this WSP, the wheel slide protection systems in each axle will ensure that it supplies the right amount of brake force which that axle can sustain, can apply without slipping.
No, not at all. WSP design is something I did. WSP has nothing to do with load transfer from the first axle to the rear axle. As long as the brake application does not involve wheel slipping, the load transfer will happen. And that is primarily because the brake pads will grip the disc brake. Once the brake pads through the friction at that point, there's a certain load transfer. The primary suspension will not move. The whole wheel has been gripped by the braking system. And this is even more true in the ICF coaches.
Yeah, no, what I'm trying to say is that the WSP system is meant to ensure that the wheel does not slip. It may, I mean, the load transfer will certainly happen. And
Mr. Salim, if
yes,
braking force is equal in all the wheels, then still there will be some offloading and unloading on the different axles.
yes, it has to be, because you are applying your forces at the rail level. Your reaction is your CG is at the top, so obviously there will be a moment which will create this offloading. Like even when you're driving a car, if you apply the brake, all 4 brakes will be seeing the same force, but you will still the brake force is same on all the 4 wheels, but the front wheel will see more vertical load than the rear wheels.
So whether this is simulated in the Simpac or a new car?
No. In
No.
Simpac, we don't simulate this phenomenon. In Simpac, What we are most worried about is the stability of the natural operation without brakes. I mean, it is like I'm able to run stable at high speeds. Yes. I'm able to curve on the tightest curve without derailing. Yes. So these are the key things that we will look in a SIMPAC simulation. We don't simulate the load transfer that happens in brakes and what happens. That may be the next stage. Maybe, I mean, I don't think we have reached to add this
Okay.
braking phenomenon into SIMPAC and see what happens to the track forces. We don't do that.
Yeah,
But
just
this
to
kind
add, let me just add a little bit to what Salim
sir.
is saying. He's absolutely right. By default, SIMPAC is only looking at the control system stability wala part. If you really want to handle the braking part, you just have to switch over to time domain, and that will bring out some of those issues, especially if you look at multi-body across two coaches. My question was actually something slightly different. It actually talked about the load factors on the primary suspension and on the bogie frame, because when the primary suspension gets shorted because of disc brakes clasping the wheel set directly, there is an extra load which comes on. Initially, when I had done that work, we had not catered for that load, and we found that the springs were actually homing. And then when we added that factor inside it, redesigned the springs, then the homing of the primary suspension stopped, and the primary suspension failures, while this was even before they were manufactured, we were very confident that the spring would not fail in primary suspension. And since primary suspension failures is a major issue right now, I was just wondering if it is being handled. If it is not handled, fine, it's okay. But this is something that RDSO would need to handle, because it is definitely a major source of spring homing. यदि वो spring दबा करके उसने पकड़ लिया है, तो धेलेवर कुछ नहीं कर सकते हो. It's caught. So that was really the issue on the first point. The second point was with regard to location of the centroid. So you had talked about the wedge test, sway test, etc., etc. But these are for static. So I'm just wondering, for the 3 radius of gyrations, are you doing any test to validate that the centroid is where the CAD system tells you, or do we just make that assumption and carry forward?
No, there is no physical test that I can recall which tells this is where the centroid lies.
Okay,
I'm
so
not.
I had done this discussion with the US railroads, and they actually had a system of validating, especially for freight stock, the location of the centroid. If it's not being done, fine, fair enough. I just really wanted to know if you guys take a look at that at all or not. So
I
that's fair
think
enough, perfectly okay.
CAD models are quite mature and quite yeah.
So they'll give you a CG very nicely, but they don't give you a
Correct.
centroid very nicely, because we don't do dynamic simulations for centroid. And it turns out that there is a fair amount of difference. At least the US railroads found a huge difference between the center of gravity or center of mass, which comes out from the CAD models, and the center of, for the radius of gyrations, which is the centroid as actually measured. So I'm just very curious. They got some large differences. Just curious if you guys ever did that. If it is not done, it's fine. I'm just curious if it was done
I'm
at
not
all
able to
or not.
recall doing that. Yeah. Sorry.
Yeah. Fair enough. Just one last question. You had talked about that FEA, and that was the thing that I directly had worked on. One of the things that we had done was that we had done a failure mode analysis. So all the points which are highlighted as possible points of failure, high stress values, etc., or high strain energy values, both of them we had looked at. We had done a crack propagation exercise out there, trying to figure out that if it fails, what would happen. And there were exercises that I had done for mitigating crack propagation. Is that an exercise which is now a standard part of bogie design or not?
No, we don't reach there. That's what see. Our EN standards does not really call for that level of analysis. It is, see, when you have a crack and propagation, it is something like a very specific case that you would do, because we are designing the rolling stock in general. We need to ensure that we don't reach a crack phase.
That's what the theory does. The problem is that bogie frame cracking is rampant currently on Indian railways. So I'm very, very curious in the newer designs, while the theory has existed for a very, very long time. Fact is that the theory breaks down, at least in India, it seems to break down a hell of a lot. So I'm just wondering if, and I had done it, and then we had actually identified possible failures, and we had done some mitigation exercises. So I'm only aware of 2 cases of bogie frame crack on the IR20 in its complete period of existence. But I'm just curious, if it is not done, it's not done. Fair enough. It's a failure mode analysis, and it normally comes out from feedback from the field. But it has been rampant, so I'm just very, very curious, both on freight and on coaching side and on locomotive side. bogie frame cracks keep happening. So I'm just curious. Fair enough.
Hmm.
If you don't do it, you don't do it. Fine. That's okay. Great. Thanks a lot here. Nice presentation. Nice to go over things that we have done. Great stuff.
Yeah.
Thanks.
Thank you.
Tanmay sir, Apurva here. As a rail fan, I believe that IR20 should have been continued. We discontinued because it was a wonderful coach.
So thank you so very much.
Yes.
I and Sanjeev Kishore will be very grateful for that. We have
Yeah.
had the same feedback because Sanjeev did the shell, etc., and I did the underframe and the structurals. So it's wonderful to hear that from.
We never needed the LHB coaches. We should have done everything in India.
Thank you.
Tanmay, my
Sir.
last visit to Amritsar was in 2005, and I saw the Swarna Jayanti, what's that, Shatabdi?
Shatabdi.
Yeah, Swarna Shatabdi, and I asked the TXR and the staff, and they were all praised for this bogie.
Thank you so much, sir. Thank you.
And of course, the body also, looked very sleek. It had that American look. I don't know why the IR20 was allowed to fail.
It was no, sir. I can answer that question. I'll be very fair. I can answer that question because I was sitting out there when the decision happened.
I suggest you answer this question offline.
Chalo. Chaliye.
Okay.
Mr. Vishwal Gupta has raised his hand. Vishwal Gupta, please go ahead.
Sir, unmute kariye. Yashpal sir.
Vishwal, please unmute yourself. Vishwal Gupta, please go ahead.
In respect of ride quality, are we still following the old ride index, or we are using power spectral density now?
We are using the power spectral density, sir. There are some EN standards, EN 12299, which defines how to convert the vibrations into the calculation of the ride quality. So we follow that standard.
So therefore, for all coaches, wagons and locomotives, it's now power spectral density.
Yes.
The ride index.
That's what I recall, because see, I recall two methods. One is called the RDSO method and one is called the EN method. That's what our team always talks about. But if the requirement clearly says that we need to follow the RDSO methodology, then we follow the RDSO methodology as defined in their MT334 document or something like that. I don't remember now if it is still current or not. So yes. And it's all like there is no more manual counting of the peaks, and they're not trying to do it manually. It's all automated. So everything goes into the computer and it just comes out. The number comes out of the computer. We don't do any manual intervention, like the cutting of the frequencies, all this done by the computer itself.
I appreciate that, but what is the Indian Railway standard? Ride index or PSD?
Sir, good morning, sir. I am AK Singh.
Hello, Singh. How are you?
I am fine, sir. Nice to see you, sir.
Very mutual.
Sir, so far we are following the riding index, and in future we shall go also as per the EN standard 1436D. But as Mr. Salim said, we shall be following again the same standard. I think 1229.
Sir, if I may just add from the IR20 side, since people have praised it, I'll just quickly add a very small addendum to what AK Singh has said. Ride index is what RDSO is using, which is fair enough. There is a reason why they are using it. But as a part of bogie design, when I was using bogie design, I used ISO comfort curves. EN standard did not exist at that point in time. So we used ISO comfort curves as the basis. And we added one element out there, which is not really very well done even in the EN standards. And that is the issue of LCR, which is lower center of roll versus upper center of roll. So while the PSD comes across very nicely from the EN standards in India, it doesn't translate to comfort because it does not distinguish between upper center roll and lower center of roll. And at least in IR20, we had discovered as a part of simulation that lower center roll, which is what makes a person seasick, is very, very prevalent because of the geometry of the Indian Railways track, both from the PSD viewpoint and as far as the geometry viewpoint. So a lot of work had to be done. In fact, I remember spending something like 15-20 days just on correcting lower center of roll, even though it made not a single difference as far as the comfort curves or the current EN standards would do. So what really needs to be done is to take whatever work has been done. The ride index has a merit because it talks about peak disturbances. EN talks about an overall average kind of a performance. And then you have to add the sensibilities of the Indian Railways. And one point I am definitely mentioning, because I know I worked so hard on getting it right, is this concept of lower center of roll, which is terrible on Indian Railways. So I would agree that all of them have a role to play. It is not this or that, it is this and that.
Right. Thank you.
Sir, one question for Tanmay sir as well as Salim. LHB coaches have such a fancy wheel slip protection. Why do we still get flat wheels? I mean, it's very common. It's 50-50 milta hai. Some of the coaches may have good wheels, but most of them do have a flat spot. So why doesn't it work in India?
Salim, you go first. I'll go after you.
I can also explain something, sir.
Yes, sir. Sir, boliye.
No, actually, we have the WSP system, but see, Indian Railway is a very vast railway, and the maintenance of the WSP has been an issue. So we have the practical experience. Once we are maintaining the WSP in good condition, then definitely the values of the wheel flat is quite reduced significantly. But still, some time noted that even in the new wheels, some flat behavior is observed. But that may, I think, maybe say a drawback of the disc brake system.
It's
Because even in the IP brake system, Vande Bharat trains, we find sometime wheel flat. So even after having all the safety devices in our coaches, sometimes we do face the problem, which is not there in the ICF of the coaches.
ICF but problem
but the quantum of this wheel selling is reduced significantly when we do the proper maintenance of the WSP. But still, we can't vouch that it will be zero. It will be there. Definitely something will be there.
Right, sir. Thank you.
Mr. S.K. Sharma had posted a question in the chat box. Please go ahead, Mr. Sharma. Mr. S.K. Sharma. Please unmute yourself and go ahead.
Yeah. Mr. Salim, as you have mentioned that a lot of electronics and sensor-based developments are taking place, that's being integrated in bogie design. So is there any concept like smart bogies that is evolving in railway rolling stock?
Yes, sir. Yes, sir. We are going to adopt this online condition monitoring system very soon in our rolling stocks, definitely.
Yes, I mean, at least from our side, all I can say is that there are some modules that we can plug and play on existing bogies, which will continuously monitor the health of the bogie.
So what shall be the parameter which you will be monitoring? Say the bearings, hunting, suspension, brakes. What can you just give us few names? What you can monitor that?
So the most basic and the primary thing is the axle box temperature monitoring.
Yeah. See, temperature monitoring is not going to give any value to us, because when the temperature of any bearing has risen, then there is no time for the response. So we must require the advanced signal if we have to react on the this axle box. So temperature monitoring is not useful, I think, at large scale.
No, what we have is, I'm just telling you the example of the most basic thing that we do. We also measure the noise and the vibrations. Like,
vibration definitely.
Yeah. So see, these are the only physical things that you can actually measure out of the bogie: temperature, vibration. I'm not able to think of anything else that we can measure.
Hunting, you can monitor this.
Right. Hunting, when I say hunting, it's again vibration. So the physical phenomenon that you measure is the temperature, vibrations, and then you try to rebuild based on your logic that okay, this is how it is working. So you will have, what you will do is maybe you will have a measurement done on a new condition of the vibrations of the temperatures or whatever, and that will be your baseline or the benchmark. You record it and place it somewhere. Then you keep on measuring over the time how this signal is changing over the time. Or maybe you also measure it in a worn out condition, and that will be your second baseline. So the reality will be somewhere in between these two baselines. So you'll continuously monitor this temperature or vibration and see where it is landing between these two baselines in a new condition and
Definitely.
worn out condition. And that is what is like continuous monitoring or smart monitoring of the bogie. And at the moment you see that it is going towards that failure, you stop it. It's basically recording the signals of recording a good signal, recording a bad signal, and keeping it as your
Sure, sure,
baseline, and
definitely.
then continuously monitoring it and see where the signal lies. Is it towards good or bad?
Salim, one question from me, Apurva. Why do the high-speed locomotives have a Bobo configuration, like only two axles? And why does the WAG-12 have a Bobo while it is a freight loco? What is the reason behind that? I mean,
Only
you says a
locomotives.
train like the Bhopal Shatabdi, it has to go,
Mhm.
Gatiman, it has to go at 160 kilometers per hour. So WAP-7 cannot run it. The new one can probably, the new version,
Mhm.
but normally it's a WAP-5. And the reason we were told is because the WAP-7 cannot go more faster than 130 kilometers per hour. So what is the reason for high speed running only on a Bobo? And why does the WAG-12 have a Bobo?
Yeah. Okay. Why high speed should be a Bobo? See, Bobo is the most stable and the most basic bogie as such. You make a Coco because you cannot manage in a Bobo. If given a choice, you'll always do a Bobo bogie and stop there. When you make a Coco bogie only in locomotives,
Okay.
because you are expected to generate the tractive effort, the hauling capacity, which you cannot generate with a Bobo. So you add another axle and then increase your hauling capacity.
Mm.
And the moment you go for Coco, the mass of the bogie increases, the complexity increases, and
Yeah.
the instability increases at high speeds. So that is why it is difficult to make a Coco run at very high speeds. Maybe up to 160 we have seen, we have made trains which run at 160 on a Coco, but beyond that, I'm not able to think of an example of a Coco bogie running beyond 160.
Okay.
So you do a Coco to generate the hauling power,
Yeah.
or maybe you're not able to manage the weight with Bobo. Like for example, you need to make a 6,000 HP locomotive, and your axle load is say 22 tons per axle. You know that when you put when you put the engine, when you put the radiator, when you put the operating cab, everything put together, you will never be able to reach 22 tons with four axles. You need six axles. So only
Right.
then you go for a Coco.
Okay.
And going for a Coco means additional traction that you can generate.
Yeah.
Uh,
So,
ca- can I
yes,
add
sir.
to that?
Yes, sir.
Yes, sir.
Please go ahead.
Apurva,
Yes, sir.
two-axled bogies on locomotives have been generally they have been failing on Indian railways. I don't know why.
Yeah.
Starting with WM1
Yeah.
and WM2, WM3, then WM4 was a three-axle bogie.
Yeah.
But we continue to perpetrate this two-axle bogie, hoping for the best. I wish the WAG-12 all success, but way back in 1978, Skoda had suggested an same type of design, that is articulated coaches with two-axle bogies, four two-axle bogies. And there's a long note in RDSO from the railway advisor, London, that this type of configuration is not recommended for Indian Railways. I really don't know why. See, WAP5, WM3, WM4, 2 and 3, they had this problem with the WN couplers. The WM1s had the problems with and the WAG4s had problems with the Jacomin drives,
Yes.
which got twisted out of shape.
Yeah.
So I really don't know. But in my experience, I have found that two-axle bogies on even WDM6, which is an ICF type of bogie, failed in the locomotive. I don't know why. Maybe because asking too much tractive effort from each axle, or I don't know.
No, it's an
If I may
interesting.
add something to that,
Yes.
Mani sir,
this is
boliye.
Mani.
Yeah.
Sir, I don't know how true this is for Indian conditions, but based on my research, when the French were initially testing out high-speed electric locomotives with the cooperation of Alstom, using Alstom equipment, so they initially tried high-speed running on Coco electrics. So
Right.
what happened? The one of the Coco electrics, I forget the number of the electric loco, that achieved an initial high-speed record for electric traction. Then what they did, they changed they asked Alstom to manufacture a similar type of a loco, but with Bobo configuration, and then it replicated the same speed. Obviously, it replicated the same speed with more stability and also lesser wear and tear to the track. So what they decided based on that research, this was way back in the 60s and 70s, was that the Bobo would be the minimum stable configuration for high speed, and henceforth it became a policy of SNCF to build high-speed electric locomotives in a Bobo configuration. But this is based on French experience, sir. This was quoted by Brian Hollingsworth, formerly of GWR, when he was actually studying French locomotives. So that's just my 2 cents over there. Thanks.
Thank you.
Let me add a little
Gentlemen,
bit
we've
if I.
already exceeded our total time.
Fine.
Yes.
So I think we should end here.
Yeah.
I'm very impressed by the very animated discussions we have had on bogies and bogie design and so on. But for this, I would like to thank Mr. Salim Basha for a very good talk, a talk that put a very technical subject in a let's say in a way which even a non-technical person would appreciate, if not understand. Well, thank you very much, Mr. Basha, and I hope you will be able to give us more such talks in the future. Also,
Yeah,
thanks to all the audience
Salim
and for
also
the
knows a lot
participation
about.
of all the people.
Yeah, Salim also knows a lot about coupler design. So maybe we can rope him in for that also.
Yeah, sure. But no, sir. I just want to say something. I think I know very less. To be frank, after talking to the questions, I mean, looking at the questions that I'm getting and the history that is popping up here, I definitely know very less, and I'll be very eager to have a like a short meeting discussions with whoever has the knowledge, so that I can improve upon my knowledge and also impart my knowledge to whoever is needing it. So I would wish to have more and more interactions with all the stalwarts here, so that the two-way knowledge sharing can happen, sir. I think there is a lot to learn. That's what I have learned in this meeting. More than teaching, I think I have learned a lot, I would say, by taking some notes based on the IR20, so on and so forth.
Yeah.
Anyway, thank you very much, everyone. I'm stopping the recording now.
Okay.
And I hope we have such talks in the future also. Thank you.
Certainly, sir.
Thank you,
Certainly.
sir.
Thank you.
Thank you, Salim. Bye.
Thank you.